Every single time electricity moves through a wire, some of it disappears. Not stolen, not wasted in a way you can see or feel or notice, just gone, converted into heat by the resistance that every conducting material in the world has always had, that every conducting material in the world was assumed to always have, that every electrical system ever built by human beings was designed around accepting as an unavoidable cost of physics. Between 8 and 10% of all electricity generated on Earth never reaches its destination. It is lost in transmission. It bleeds into the air as invisible warmth from power lines stretched across continents, from cables buried under cities, from wires inside every building and every device. In a world consuming over 28,000 terawatt-hours of electricity annually, that loss represents more electricity than the entire continent of Africa uses in a year. Vanished. Every year. Because of a property of matter that has resisted every attempt to overcome it at practical temperatures since superconductivity was first discovered in 1911. And on June 29, 2026, a team of scientists published a paper in Physical Review Research announcing that artificial intelligence and quantum physics calculations had together identified two materials that should not, by the conventional understanding of how superconductors are found, have been found. Not yet. Not this way. Not this fast. What happened on that day is not the end of the story about room temperature superconductors, but it may be the moment we look back on as the beginning of the end of a 115-year search. And understanding what it means requires understanding something that almost nobody has explained clearly about why this discovery is different from every previous superconductor announcement that has come before it. Let me start with what superconductivity actually is, because the explanation you have probably heard does not capture the thing that makes it so extraordinary. Every material you have ever touched has electrical resistance. When electrons move through a wire, they collide with the atoms of the material. But even copper loses energy. Even the best conventional conductors lose energy. This is not a design flaw or an engineering limitation. It is a consequence of how electrons and atoms interact at normal temperatures. Superconductivity is something completely different. Below a certain critical temperature, some materials undergo a quantum phase transition. The electrons stop behaving as individual particles colliding with atoms and start forming what are called Cooper pairs, bound together by quantum mechanical interactions. These Cooper pairs move through the material in a collective quantum state called a condensate, and in this state, they do not interact with the material's atomic structure in the same way. They do not collide. They do not lose energy. Current flows through a superconducting material with literally zero resistance. Not low resistance. Zero. A current set in motion in a superconducting ring will continue flowing indefinitely without any power source, without any energy input, without any loss, for as long as the material stays superconducting. This has been demonstrated experimentally. It is not theoretical. Superconductors exist, and they do exactly what the theory says they do. The problem is the temperature. The critical temperature below which superconductivity appears is, for the materials we have known about longest, extremely cold. The first superconductor discovered was mercury, and its critical temperature is 4.2 Kelvin, which is 4.2 degrees above absolute zero, the coldest temperature that can theoretically exist. That is colder than outer space. Achieving and maintaining those temperatures requires liquid helium cooling systems that are expensive, mechanically complex, and consume significant energy themselves. The superconducting magnets in MRI machines, the superconducting components in particle accelerators, the superconducting elements in quantum computers, all of them require elaborate cryogenic infrastructure. They exist because the applications they enable are valuable enough to justify the cooling overhead, but they cannot be deployed everywhere. You cannot build power lines out of a material that needs to be cooled to near absolute zero. You cannot build consumer electronics with superconducting components that require liquid helium. The extraordinary properties of superconductors are locked behind a temperature barrier that makes them useful for specialized applications and completely impractical for the transformative applications that would change civilization. The holy grail of condensed matter physics for over a century has been a room temperature superconductor, a material that exhibits zero resistance at the temperatures found in an ordinary environment. If such a material existed and could be synthesized at scale, the implications would be difficult to overstate. Power grids rebuilt with superconducting transmission lines would eliminate that 8 to 10% annual electricity loss immediately and permanently. Magnetic levitation transportation at practical cost. Computing systems that generate no heat. Energy storage that loses nothing. MRI machines that cost a fraction of their current price and could be deployed in every hospital. The International Energy Agency has estimated that superconducting power transmission at scale would save enough electricity annually to power the entire United Kingdom for a year, every year, indefinitely. This is not a marginal improvement. It is a physical transformation of how human civilization relates to energy. The reason this discovery matters is not that room temperature superconductivity has been achieved. It has not. The two materials discovered by the SuperC Consortium, named YRU-3b2 and LURU-3b2, are superconductors at critical temperatures of 0.81 and 0.95 Kelvin, respectively. These are extraordinarily cold temperatures, colder than most known superconductors, and nowhere near room temperature. If you read a headline suggesting this discovery means room temperature superconductors are imminent, that headline is wrong, and I want to be clear about that before anything else in this story. What matters about this discovery is the method, and the method is the thing that changes everything. For over a century, new superconductors were found essentially by accident. Researchers would modify a known superconducting compound, test it, find that either worked or did not, and move on. The process was described by Professor Päivi Turma of Aalto University, who leads the SuperC Consortium with a directness that captures how crude it has always been. Over the decades, researchers have recognized over 7,000 superconductors, but mostly serendipitously. 7,000 materials in 115 years of active searching. 7,000 out of a search space that, when you count the possible combinations of elements, compounds, crystal structures, and compositions that could theoretically be tested, is effectively infinite. The traditional method was not really a method. It was controlled guessing with expensive equipment. The SuperC Consortium did something different. They combined two technologies that did not exist at the scale required for this application until very recently. Machine learning algorithms and quantum geometry calculations. The workflow they developed operates in two stages. First, machine learning screens an enormous combinatorial search space, evaluating the theoretical properties of vast numbers of candidate materials far faster than any human team or conventional computational method could. The algorithm does not run experiments. It evaluates theoretical properties, identifies patterns in the quantum structure of materials that correlate with superconducting behavior, and flags the candidates most likely to exhibit the properties worth investigating further. Second, those flagged candidates undergo detailed quantum physics calculations based on a framework called quantum geometry, which the SuperC Consortium has been specifically developing to understand the quantum mechanical conditions under which superconductivity emerges. The most promising candidates from that second stage are then synthesized physically in a laboratory and tested experimentally. In this case, the synthesis was done at Rice University, and the experimental confirmation that both materials exhibited bulk superconductivity was the result published in Physical Review Research on June 29th. Professor Turma stated that this method could enable processing billions of materials, something that was completely impossible with any previous approach to superconductor discovery. The significance of that number is not about this specific pair of materials. It is about what the pipeline itself represents. A systematic, AI-guided, quantum theory-grounded method for searching the chemical universe for superconductors replaces a century of serendipitous discovery with something that operates more like engineering than luck. The SuperC Consortium was founded in 2023 with the explicit goal of finding a room temperature superconductor by 2033. That timeline, which would have sounded fantastical stated as a serious scientific objective in 2020, is the deadline they are now working toward, with a pipeline that has proven it can find real superconductors that were previously unknown. To understand why the AI component specifically matters here, it helps to understand what Google DeepMind's GNoME project demonstrated about AI and materials discovery at scale. GNoME, which stands for Graph Networks for Materials Exploration, used deep learning to predict the stability of 2.2 million new crystal structures, an amount of materials knowledge that DeepMind estimated would have taken approximately 800 years to generate through traditional research methods. Of those 2.2 million predictions, 380,000 were confirmed as among the most stable known material configurations. The database includes 52,000 new layered compounds similar to graphene, many of which have potential superconducting properties, a category where previously only around 1,000 such structures were known. External researchers at laboratories around the world independently synthesized 736 of GNoME's predicted structures in concurrent work, confirming that the AI predictions were not theoretical artifacts, but real materials that can be made in a laboratory. In 2026, several academic labs have reported experimental synthesis of additional materials predicted by GNoME, and DeepMind has made the database publicly accessible to accelerate independent verification across the global scientific community. The SuperC method and GNoME represent two parallel tracks of the same fundamental shift. For a century, the number of materials humans could investigate was limited by human time, human intuition, and the speed of experimental synthesis and testing. AI has removed the first two constraints. Quantum physics calculations have made the third constraint dramatically more selective. The combination does not guarantee that a room temperature superconductor will be found by 2033. What it does is transform the search from a lottery into something that looks much more like a systematic investigation of a finite, mappable territory. Here, I need to talk about the history that makes honest assessment of superconductor claims important. Because this is a field with a complicated relationship between announcements and reality. In 2023, a team of South Korean researchers announced that a material called LK99 was a room temperature ambient pressure superconductor. The announcement went viral across the scientific and technology community.